Hello, Wizardus here. Welcome back to another part of this Linux crash course. Today, we'll dive deeper into processes. We'll learn how they work, how to use them to our advantage, and more. Alright, that's it for the intro. Leave a quick like, subscribe to the channel, and off we go. But first, let's recall what do we know by now. As you see, the list has grown since the last episode. If you're new here, or any of these terms still look mysterious to you, check out previous videos and come back here later. But let's start from the beginning. What is a process? To simplify it, it's an instance of a running program. So for example, when last time we run commands in the shell such as cat or ls, our shell created a process that terminated after giving us the results. This were the examples of foreground processes. They are attached to terminal session and more or less require user interaction. We also have background processes that can run independently without direct user interaction, aka blocking a terminal. Process, or a task, is represented as a task struct data structure. As the name says, they store data. Here, information about the process. Some of the most important ones are listed here. Let's start with PID. It stands for process ID and is a unique identifier for the process. There will never be a case when two different processes have the same PID. Next is PPID. It's an ID of a parent task, such as the shell, some app, or root process, aka init. UID is the ID of a user that this program runs as, so it has all the permissions of such user. GID is pretty much the same as UID, but instead of user, it stores ID of a group, which such process runs as. Then, also memory allocation, this is just a bunch of data that says how much memory and what type of memory, heap, stack, or whatever else, the process uses. But there's also process's state. There are many such states. Actually, when the task is ready, it starts as running task. Then, when waiting for something, event or resource, it goes into waiting state, also called a block state. These tasks can vary depending on what they wait for. If a task is interruptible, you can send it a signal such as SIGTERM and it will terminate. This input is mostly used when waiting for user input. But there are also uninterruptible tasks. To be exact, uninterruptible sleep, which cannot be terminated with a signal such as SIGTERM or even SIGKILL. Only way to kill it is to reboot the device. Why? Because they mostly handle and interact with hardware, and such termination would cause severe data corruption. Also, tasks can be stopped. So when we send a signal such as SIGSTOP, it will halt running and allow us to, for example, debug it via memory dump or something. But there are two more of an error process statuses. First, it's a zombie task. It's a terminated process that still has its entry in process table, as its parent is yet to read exit status. Just like zombie, it's dead but still alive. Linux also has orphans, processes whose parent is either terminated or finished. They are then typically adopted, quote unquote, by init or systemd process, so they don't turn to zombies. By the way, do you recall /proc directory from one or two episodes ago? Yeah, the one with virtual dirs and that only exists when you run the OS. Today, let's dive a bit deeper in that and see a couple useful files that can be inside process/pid or process self, which is a symlink that leads to the directory of the calling process. The most important one here is status file, just like you see here on the right. It gives us all the info about the process, UID, GID, state, what command does it run, etc. in a nice to read form. Then, let's see stat. It will give us weird string of numbers that represents also statistics, such as PID, state, name, and more. It's like /status, but easier for machine to read and use the data. Next one is /conf file, just like you see here. It gives us the binary that was run with that process. Yeah. In our case, it returns cat, just like in the picture below. Another important one is limits. It informs us how much resources can one process utilize. Let's take Observer as an example. You can open many files at once, but this number is fixed. Otherwise, we'll get error, just too many open files. And the last one I'd like to mention, just briefly because we talked about it last time, /proc/pid/nvrun. It's a file that stores all the environmental variables that this process can access. Right now, there's only one thing left, and I want you to know it because it's a typical Linux terminology. I'm talking about daemons, background processes that run independently of user sessions. You'll find them most Linux servers, scheduled tasks, or overall things that will run for a longer period of time. As for the naming convention, daemons processes are mostly appended with letter D, that stands for daemon. For example, if you like here, SHD, systemd, HTTPD, crond. As they run in the background, they don't really need any additional user input. Alright, with all that theoretical basics, we can jump straight into our Debian and test our knowledge in real life. Alright, now in our lab, let's maybe start with starting a process. It's nothing much simpler than just running a command. So just ls, hello, you have just now created a process. But what if you want to start a background process, not the foreground one? Because if you run, for example, netcat with some L, B, and P, 1, 2, 3, 4, it's going to take up our whole terminal, and we don't really want to do that. Alright, let's kill it, Control and C. And we can also append this little end behind. That's how we get the process ID. And our terminal is not blocked. To foreground it, we can just type in FG, and here is now back. We can also background it again using Control and Z. That's a little bit backgrounding, but stopping the process. And the foreground will bring it up again. Alright, let's do it. Then, when we know how to start a process, start a background process, and more or less kill it, let's maybe check what processes are even running. We can do this using process status command, aka PS. It displays information about processes that are bound to control a terminal, if we type in it like this. So right now, there is netcat, there is bash, and there is some process. We have already PIDs here. Beautiful, but this is not always the case. Let's maybe also look at these things here. PID is the process ID. Pretty simple, pretty straightforward. You know what it is from the theoretical intro. TTY is the terminal that is associated with process. If we type in just PS, these are all the terminals associated with us. These processes are just our terminal. Then time is not a time process running, sadly, but it's a CPU time of a process. CPU time is just the amount of time that the central processing unit was used for processing instructions of a computer program or OS. But PS is not always run without any arguments. If we add, for example, A, we can see all the processes running from all the users. We can stack those processes. For example, if we add the U, which is then going to return us additional information. It's just start, all the statistics, so what the status process is. Then X, if we append, returns us the info about terminals. And also a bit more of processes. With the extended info, as you see here, there's a fair share of it. In this configuration is what you're going to use the most. Also using ps-ef, we can see this little question mark here, which processes are demonized. As you see here, for example, systemd network D is demonized. We can see by this little question mark and D right here. But now let's say we have this process running, but we don't want it. We want to kill it. That's why I suppose another command. Kill command is going to terminate a process by sending them some system code. By default, it's SIGTERM. So if we type in kill, let's kill this netcat right here. We're gonna kill 40, 60, and the process is dead. If we type in PS, as you see, we just have PS and bash, and that's it. You can send all the different codes with kill. To list all the codes and signals, you can type in -L, as you see that there is a fair share of it. But for us, apart from SIGTERM, which definitely is somewhere right here, the most important one will be SIGKILL, because when the process does not really want to get killed, you can type in kill -9, which, as you see here, means SIGKILL. Also, with -p, you can just print the PID of a named process, but don't kill it. Named processes are a bit of different things. I'm going to probably make another video on them, like a short or something. But right now, let's go back to our Linux, because there are plenty of other options. Apart from ps, we can also use top command. Here, if we just run top, you can see we have this really cool, more or less, task manager from Windows. You can dissociate it like this because we have, for example, info about memory, CPU, processes, running, sleeping, zombies. And you can navigate it via arrows. Arrow up is going to get you somewhere up. Arrow down is going to move you down, right and left. And using Q, we can just exit it. We just click on Q. Another things I'm going to talk about is df and free. df is a command that says how much disk space is being used by the file systems. For example, here I have this def sda, which is my main file system. It's stored in it means 1 kilobyte blocks, how much is used, how much is available. There's a fair share of it, let's put it this way. I have 30 big VM. But yeah, there's also free command, where it shows us all the information of memory, which is how much memory is used in the system. But the last command I want to mention is a really nice command. Yeah, because the command is called nice. Linux runs more processes than there are cores of CPU, so it's almost them around there. So it feels like the processes are run simultaneously. To manage how these processes will be passed around, they get assigned a process scheduling policy on a 40-point scale to measure their niceness, from -20 being the highest priority and to 19 being the lowest. To explain it simply, the bigger number a process has, the nicer it is, so it will more gladly share its resources. So if the process has niceness of, for example, 17, it's going to be nice and swap with our process. But if the process is -20, it's going to stick to the CPU, it's going to stick here. In top command, it's in the third column. You can see here niceness, for example. You can see it here. This is the NI. There are plenty of tasks with -20, which means they're not willing to give up their CPU. Only root can increase their priority. So if I try to change it, and I was the wizardless user, I'll just get permission denied. User can only decrease the priority. To reassign niceness to a program, we can use renice command. Let's say we start another background shell, lvnp, nano, whatever. Alright, let's type in just some a bit of random port. Alright, then it's working, but we need to run the background, so it gives us the PID. Right now, it's just PID 409. We can use it with ps-aux. As you see, we have the process right here. And using top command, we can check its niceness. Let's go down, all the way down until we find our little netcat somewhere down there. Plenty of processes have niceness 0, as you might see here. We're going down, down. I hope I did not miss it, by the way. But yeah, it's going to be fine. You see, here it is, process ID 49090, and it says niceness of 0. Let's maybe quit this, and if we try to renice it with nice value, let's say -10, and then 4999, we get permission denied. Why? Because we are not root. But if we try to change it to, for example, 10, works like a charm. And now in top command, you can see that, let's scroll down a little, we'll see that, yeah, this process is such niceness, and it works like that. So yeah, I'd say that's everything about processes. Thank you so much for watching. I hope you enjoyed it. let's stay here for a second because we're gonna see the niceness of the process. In the meantime, you can leave a like, subscribe to my channel, well, maybe share some positive comment and share our message on what I'm doing here outside with your friends. I appreciate that. And you see here, niceness has been changed to 10. And yeah, that's really about it. Again, thanks so much for watching, and see you next time in another, this time also very important video. Cheers!